Hey guys, so we have moved considerably from our starting point. We began by considering a crystalline system that is experiencing a force, and we just wanted to understand under such a condition how my position of the atoms are going to change with respect to my time. So we translated that physical problem to this expression here, and we built a tool to solve this expression. And of course, to make our life a bit more complicated than it already is, we introduce an additional influence. We said that the force experienced by the atom no longer depends on its position alone, but also depends on the velocity with which it is moving. So we came up with an expression, or that physical consideration rendered us an expression something like this. Of course, this is a generalized expression wherein the f of x indicates the position of the atom. Now, when we used the tool that we originally developed to solve this expression here, to understand or to arrive at a solution for the position of the atoms in this case, we found that the approach became rather a bit too tedious. So we adopted something called as a street fighting technique, wherein instead of just assuming the form of the solution and assuming it to be smooth and continuous, we directly assumed the solutions and we were able to solve this expression here. So once we made that assumption of our solution, everything was rather smooth sailing. We were able to arrive at something called as a characteristic equation, and everything from that we were able to arrive at the solution. However, we faced a critical problem. We reached something called as an impasse, wherein the solution this approach rendered were not just one unique solution, but rather two different solutions. Of course, had it been a pure math problem, this would have been fairly comfortable to us. Of course, a math equation can have two different solutions. Unfortunately, the equation that we are trying to solve has a physical significance. So when I have two different solutions, what it essentially means is at a given time t, it is possible for my one atom to be at two different positions. Of course, we are not talking in quantum mechanics level, it's atoms. So still we are in the classical mechanics, so we cannot have such a solution, it is not valid. So therefore, what we did, we used the property of mathematics that related to the nature of the ODE we solved to arrive at one unique solution. Again, we looked at the ODE we solved, we understood its form, and based on the form, we used a mathematical understanding to come with one unique solution. Now, that mathematical understanding, we were able to use it because we were able to identify the ODE we solved as linear and homogeneous ODE. We were able to identify this ODE that we solved as linear and homogeneous ODE, which now we will be representing as H. And since when our ODE that we are solving is linear and homogeneous, even if we have two different solutions, if the ODE is linear and homogeneous, we can have one unique solution from that by summing these two solutions up. So therefore, while we took this shortcut, even though we arrived at two different solutions, we were able to come up with one solution by summing these two solutions up. That was possible primarily because we have a linear and homogeneous ODE, or we solved a linear and homogeneous ODE. So what it essentially means is, the way we treat the solution, the approach we adopt to solve a given ODE depends on the mathematical nature of that ODE. It depends on the nature of the ODE that reflects our physical problem. If the ODE that reflects our physical problem is linear and homogeneous, now we know a solution, we know an approach to arrive at the solution for it. Now, if on the other hand, if our solution of the ODE is not linear and homogeneous, then it is rather important to note that we might have to take a different route to solve this expression here. So therefore, before proceeding any further, we need to understand the linear homogeneous ODEs from all the different forms of ODEs, from all the rest. So now, when I have something called as a linear and homogeneous ODE, it's rather natural to assume that there will be something called as, when I already have a linear and homogeneous, it is natural for us to have something called as a linear and a non-homogeneous ODE. And when I have a linear ODE, it is also possible for me to have something called as a non-linear ODE. So what essentially we will be doing in this session is, we will try to rather understand What are these different types of ODE? Again, primarily because depending on what type of ODE that we have before us, the approach we take to solve it will vary. And for that reason alone, in this context or in this series of lectures, we will spend some time on understanding or differentiating the different forms of or the various forms of ODE. Now, when you consider, so this is, as we saw, a linear homogeneous ODE. So when you want to have a generalized representation of a linear homogenized ODE, it can be expressed in this way. So what you essentially find is you have a function, you have first derivative of the function, second derivative of the function, third derivative of the function, and the nth derivative of the function. And each of these derivatives have their own coefficients associated with them, and all these are equated to 0. So when these conditions are satisfied, we refer to those as linear and homogeneous ODE. So this is a generalized expression, a generalized way of representing the linear and homogeneous ODE. And in this generalized expression, what we find is, we find a function, we find the various derivatives of the functions, and there are coefficients associated with these various derivatives. So, and all these are equal to 0. Or when you sum it up, all these are equal to 0. When these conditions are satisfied, we refer to them as linear and homogeneous. Functions, derivatives, coefficients, sum it all up, you will have, with all sums up to 0, we call those as linear and homogeneous ODE. Anything that deviates from these expressions here, we refer to them as either nonlinear ODE or linear non-homogeneous ODE. Any deviation from this generalized expression here, we refer to those as either nonlinear ODE or linear and non-homogeneous ODE. So how can we differentiate between these two is what we will see in the subsequent slides. Now, let us consider the set of these examples of different ODEs that we have before us. After that, we can be considering the first one. Now, in all these sets of expressions, we find that the ODEs, each of these ODEs are defined with respect to a function y. And this function, or the derivative of this function, is represented as y prime, y double prime, and so on and so forth. So basically all these ODEs are expressed, or they are described based on a function y of x, and their derivatives are represented as y prime and y double prime, and so on and so forth. So it means the ODEs are based on the function y of x. So therefore we can refer to y of x as the base function. And in this base function y of x, we have a fundamental variable or the primary variable, that is x. So I see a set of ODEs. Now in these ODEs I'm able to identify my base function and my primary or the fundamental variable. Now let us consider my first ODE and compare it to my generalized form of linear and homogeneous ODE. So I have my base function, I have the derivative of the base function, first derivative and second derivative, I have the coefficients, and the sum of all these is equal to 0. So I have my base function, derivatives of the base function, coefficients, and summing up all this gives me 0. So basically this adapts the form of the generalized expression here. So this is a linear and a homogeneous ODE. Now let us take this expression here. Of course, I have a base function y of x. I have a derivative of it, so y prime. Now, and the sum of these terms is equal to 0. So seemingly, this template, this trend in the generalized expression is rather fulfilled in this ODE as well. However, one key difference is, as opposed to having a constant coefficient, I have a coefficient that is a function of my primary variable. So in this case, my coefficient is no longer constant, but it's a function of my primary variable. My base function remains undisturbed, my y remains undisturbed, but the coefficient adapts a form. Instead of being a constant, it adapts a form of a function of my primary variable. Now, since my y function or my base function is similar to that of the generalized expression here, and the summing up all these expression or all these terms is equal to 0, this ODE still remains linear and homogeneous. So let me repeat, since my base function does not deviate from this template here, and sum of all these terms is equal to 0, my ODE still remains linear and homogeneous, even though instead of having a constant coefficient, I have a coefficient that is a function of my primary variable. So it means it doesn't really matter whether my coefficient is a constant or a function of my fundamental or primary variable. As long as my base functions adopt the form of this template here, that is my base function and its derivatives are involved and they are summed up to 0, what I have is a linear and a homogeneous ODE. Now let us consider this expression here. So in this case I have fifth derivative of my function. So this is nothing but or equivalent to that of 5 primes, y 5 prime, and I have y prime here. So the form and summing of these two is equal to 0, and again here instead of a constant coefficient I have a function with respect to my primary or fundamental variable. So these two are of similar form, so therefore they are also linear and homogeneous ODE. So the nature of my base function is unaltered, their sum is leading up to 0. Only difference is instead of the coefficients being constant, the coefficients are now a function of my primary variable, so it means it still remains a linear and a homogeneous ODE. Now let us consider this ODE here. Now the base function, the form of the base functions remain unaltered, the coefficients are luckily for us, they are constant. The only primary difference here is the coefficients are constant, the base functions are just in the form of derivatives. The only difference here is the sum is no longer equal to 0, but it is equal to 7. So that is where these two, the original generalized form and this equation under consideration vary. So since the sum is no longer equal to 0, so even though it is linear, it is non-homogeneous. So basically the linearity comes from how we are handling our base functions. If my base function remains as it is, or just the derivative of my base functions are involved, then my ODE is the linear ODE. Let me repeat. If my base function y of x remains as it is, or only the derivative of my base functions is involved in an ODE, we refer to it as the linear ODE. If the sum of it is equal to 0, we refer to as linear homogeneous. If the sum is not equal to 0, we refer to it as a linear non-homogeneous ODE. Now let's take this case here. Again, I have my base function and its derivative. There is no other function of my base function, and I have a coefficient that is not a constant but a function of my fundamental variable. So as things stand now, it is still linear and homogeneous, but the only key difference is the sum is no longer equal to 0, it is equal to, or it has some additional term, so therefore it is linear and non-homogeneous. So the linearity stems from the base function. The homogeneity, the homogeneous or non-homogeneous, is based on how the sum reflects. If the sum is equal to 0, we then end up having a homogeneous function. If it is not equal to 0, we end up having a non-homogeneous function. Now let us just consider the final ODE here. Now in this case, there is a function of my y of x. Now instead of treating my base function as it is, this ODE considers a function of my base function. So the nature of my base function is totally distorted in this ODE here. So therefore this turns to be a nonlinear ODE. So to sum it up, when I have a ODE, it is possible for me to realize my base function and the primary variable. When the ODE just involves base function and its derivative, and the sum of the base function and its derivatives along with its coefficient is equal to 0, we refer to it as a linear homogeneous ODE. My ODE has base functions, coefficients, and its derivative, of course, base functions, its derivative and its coefficients. I sum it all up. If it is equal to 0, I have a linear and a homogeneous ODE. If the sum is not equal to 0, then I have a linear and a non-homogeneous ODE. Now my ODE, if it involves my base function, its derivative, and also a function of my base function, the nature of my base function is distorted by introducing a function of my base function, then I ultimately end up having a non-linear ODE. So then all these are linear and homogeneous. These are linear and non-homogeneous, and this is a non-linear ODE. So let me give you a couple of examples. Maybe you can try it on your own. So what will this be? Will this be a linear or a homogeneous ODE, linear non-homogeneous ODE, or a non-linear ODE? Maybe you can try this for yourself. And maybe one more example. Yeah. What would this be? Will this be a linear homogeneous, linear non-homogeneous? What would this be? So maybe if you are able to solve these two, if you are able to convincingly state what is the nature of this ODE, then you might, or you rather have understood how to differentiate linear and non-linear ODE. Pardon me, this session has primarily been a bit mathematical and rather just for us to understand the difference between different definitions. But still it is vital because it helps us identify an approach to solve the physical, the expression that defines our physical problem. Of course, it's not always the case that the physical problem that we are facing will give us an easy linear homogeneous ODE. It might be the case that the physical problems that we are studying might render us a linear non-homogeneous ODE or totally a non-linear ODE. The first step towards solving such a physical problem is identifying what type of ODE it is. So only when you identify what type of ODE it is, you will be able to adopt the appropriate technique to solve this. So with this understanding, we will proceed by considering the different forms of ODEs and how we can solve them. Goodbye.